Imagine trying to push like the entire contents of a Blu-ray disc down a wire every single second. Over a few feet, that's easy.
Oh yeah, simple.
But over 6 miles, I mean, the physics of copper wire just, well, completely breaks down.
Exactly. Copper wire suffers from capacitance and resistance. If you try to push massive, uncompressed, high-definition video data too far, the signal just loses energy.
It just kind of dies out.
Right. The ones and zeros literally smear together until the data is just completely unreadable.
Welcome to today's deep dive. For you listening, we're pulling from a highly technical product page from HDTVSupply to demystify a device that solves this exact problem.
Yeah, the AJA FiDO-TR.
Right, the one-channel 3G-SDI LC single-mode fiber transceiver. It's a bit of a mouthful, but our mission today is to figure out how the broadcast industry pushes flawless video over staggering distances without a single glitch.
Well, the FiDO-TR basically bypasses electrical resistance entirely by acting as a real-time translator. Because instead of trying to force, fluctuating electricity down a copper cable, it takes that standard SDI video signal and converts it into light.
Wow, into light.
Yeah, it pulses a laser down a glass tube that's literally thinner than a human hair.
Which brings us to the connection type. It uses a single-mode LC fiber connection. So, why does the single-mode part matter here?
Well, it's basically the secret to the distance. You see, multi-mode fiber is thicker, and it allows light to bounce off the interior walls of the cable as it travels.
Oh, okay. Makes sense.
But that bouncing causes the signal to spread out and degrade over long distances. Single-mode fiber, though, is incredibly narrow.
So it just shoots straight.
Exactly. It shoots one intensely focused beam of light straight down the center. And because it isn't bouncing around, that signal can travel up to 10 kilometers.
That's insane.
Yeah, over 32,000 feet without losing any fidelity.
Wait, hang on, though. If you're running a continuous cable over 6 miles across, like a rainy city block or a stadium packed with high-voltage lighting,
Right.
aren't you essentially building a massive lightning rod for electrical interference? Like, aren't there massive electrical hazards?
Oh, if you were using copper, absolutely. That is a huge headache in broadcasting, specifically because of what we call ground loops.
Okay, ground loops.
Yeah, when you connect two pieces of electrical equipment miles apart, they often have slightly different voltage potentials. And that difference actually forces an unwanted electrical current to flow through your video cable.
Which I imagine creates that annoying hum or literally tears your picture apart, right?
Exactly. But because we're using optical fiber here,
It's just light in a glass tube.
right, it creates inherent electrical isolation. Glass literally cannot conduct electricity, meaning ground loops and electromagnetic interference from nearby equipment are, well, they're physically impossible.
That is wild. And you'd expect a device doing such heavy lifting, managing 10 kilometers of laser pulse data, to need massive cooling fans or a huge power supply.
You really would.
Yet looking at the specs, this transceiver is a total engineering paradox. It fits right in the palm of your hand and runs on just 3 watts of power on like a 5 to 20 volt DC supply.
It's incredible, honestly.
You can mount it directly onto a camera rig or slip it behind a crowded server rack.
And for $845, it is a bidirectional dual-channel powerhouse. But the real magic inside that tiny, low-profile enclosure is actually what it preserves.
Because it's not just a dumb pipe-firing light.
Exactly. It perfectly translates the complex SDI metadata with virtually zero latency.
So the HDR, the high dynamic range, stays completely intact.
Right.
The color grading, the contrast, all those tiny micro adjustments from the camera operator hit the production truck instantaneously from 6 miles away.
Precisely. The picture looks exactly the same on the receiving end as it did the millisecond it left the camera lens.
Next time you're watching the Super Bowl and see a pristine slow-motion HDR replay from a camera mounted on a wire 300 feet in the air.
Yeah, you aren't just looking at good camera work.
Right. You're looking at data that was chopped into photons and fired through microscopic glass by a tiny 3-watt box.
It really is the invisible infrastructure making the modern media landscape possible.
Which leaves you with something to ponder. If a tiny low-power box can instantly beam uncompressed HDR video across 10 kilometers of fiber optic cable, how will this invisible infrastructure completely reshape the future of live remote events in our cities? Could the control room of the future be in a completely different time zone than the event itself? We'll leave you to think about that.